Recently, something remarkable happened in the quiet deserts of New Mexico. Astrophotographer Sattoru Marada, working with nothing more than a 0.2-meter telescope and a meticulous scientific workflow, captured what many researchers now consider the most revealing image of 3I Atlas ever taken. It didn't happen by chance. Marada collected 24 separate 60-second exposures, each one carefully calibrated, and then processed them using advanced sigma clipping techniques, methods normally reserved for professional astronomical institutions. By removing noise, isolating consistent signals, and stacking the cleanest data, he produced a photograph with details so sharp, so coherent, that it immediately caught the attention of scientists worldwide. But this wasn't just another pretty deep sky image. This wasn't something you post on social media and move on. Because the moment researchers saw the final composite, they realized it revealed a level of structure and behavior in 3I Atlas that simply shouldn't exist, not under normal cometary physics, not under any model we currently use, and certainly not in an object traveling through our solar system from interstellar space. In other words, Marada didn't just take a photograph. He opened a door into a list of anomalies that would force astronomers to revisit assumptions, rewrite interpretations, and question whether 3I Atlas is truly behaving like any comet we've ever studied, or whether it belongs in a category entirely its own. And everything that follows in this investigation begins with this image. Once scientists began studying Marada's image, one feature stood out immediately, something so striking that it dominated every discussion that followed. The tail of 3I Atlas stretches an astonishing 2.6 million kilometers. That's not a poetic exaggeration. That is a measured physical length. To appreciate that number, consider this. 2.6 million kilometers is 7 times the distance between Earth and the Moon. If you somehow placed a highway along its entire length and drove it at full interstate speed without stopping, it would take you more than 3 years to reach the end. But the length alone isn't what shocked researchers. It's the shape. This tail remains narrow, razor straight, almost unnaturally confined for its entire unimaginable span. There is no widening cone, no gentle diffusion, no chaotic turbulence. Instead, every particle seems locked into an organized, disciplined column, as if following a single invisible roadway through space. And here's why that matters. Under normal cometary physics, the behavior should be wildly different. Large dust grains follow ballistic trajectories and naturally spread out into a broad cone behind the nucleus. Smaller grains get pushed by solar radiation pressure, forming wide, fan-shaped structures. Over millions of kilometers, these effects compound, producing tails that grow wider and more chaotic the farther they extend. But Atlas isn't doing any of that. Every particle, large or small, appears to remain in tight formation, maintaining its position with a precision that no known natural mechanism should be able to enforce over such vast distances. This leaves scientists with two possibilities, neither of which are easy to accept. 1. The dust grains are almost perfectly uniform in size, an extremely unlikely scenario for any cometary object. 2. Some kind of organizing force is preserving the structure far longer than expected, something strong enough, consistent enough, and stable enough to counteract solar pressure and ballistic spreading across millions of kilometers. Neither explanation fits comfortably within our current understanding. But the more researchers examined the image, the more they realized the tail was only the beginning of the anomalies. If the impossibly narrow tail of 3I Atlas was the first red flag, the next discovery was even more unsettling. Because when scientists enhanced Marada's image and analyzed the illumination pattern around the nucleus, they realized something extraordinary was happening. 3I Atlas is firing multiple jets in completely opposite directions. Some jets are pointing toward the sun, something we expect from natural sublimation where solar heating hits a specific active region. But other jets are pointing away from the sun at the very same time. And several of these outflows create patterns so symmetrical, so cleanly divided that they resemble a deliberate geometry more than the chaotic gas vents we see in typical comets. In normal cometary behavior, outgassing is messy. Jets emerge randomly, weaken, strengthen, rotate out of view, and interact with sunlight in unpredictable ways. But Atlas shows a strange dual-jet structure, simultaneous, seemingly balanced, and unusually persistent. Then comes the antitail. An antitail is not a supernatural phenomenon. It's a known optical effect. When Earth crosses the plane of a comet's orbit, large dust particles can form a spike that appears to point straight toward the sunday. These structures are usually temporary, lasting days, sometimes only hours, because they rely entirely on a very precise viewing geometry. But the anti-tail of 3I Atlas isn't fading. It remains sharp, it remains structured, and it remains stable far longer than cometary mechanics say it should. For that to happen, two things would need to be true, both extremely unusual. 1. Atlas must be emitting unusually large particles, consistently and directionally. 2. Those particles must be organized in a way that resists dispersion, even as they travel through the orbital plane. At this point, scientists weren't just seeing isolated anomalies. They were seeing a system of behaviors, each one improbable on its own, but collectively pointing to something far more complex than any cometary model predicted. And that growing list of anomalies demanded explanation. With each new anomaly revealed in the data, the scientific community found itself split into three major schools of thought, three frameworks that attempt to explain what we're seeing. None of them are perfect. All of them require some form of compromise. But together, they represent the most serious effort yet to understand 3I Atlas. 1. The extreme but natural explanation. This is the most conservative hypothesis, but ironically, it requires the most extreme version of natural cometary physics we've ever considered. Under this framework, Atlas is still a comet. Just a comet operating at the very edge of what physics allows. Researchers proposing this explanation argue that the nucleus might contain unusual concentrations of highly volatile ices, particularly carbon monoxide and molecular nitrogen. These substances sublimate at temperatures far lower than water ice, meaning Atlas could maintain strong outgassing even far from the sun, producing sustained jets and long-lived structures. They also suggest the nucleus could be exceptionally dense and rigid, allowing it to resist the torque forces that normally destabilize a comet's rotation. The bright reflective patches may be exposed layers of volatile ice, while the rhythmic cyanogen bursts could come from deep fractures that activate whenever rotating sunlight hits them. If true, Atlas would still be natural, just extraordinarily rare. A statistical outlier of cosmic proportions. 2. The observation and geometry explanation. The second group argues that many of the apparent anomalies may not be anomalies at all, only illusions created by the angles at which we observe Atlas. From Earth's perspective, the line formed by the Sun, the comet's orbit, and our viewing angle creates a very unusual geometry. Under these conditions, a tail might appear narrower than it really is. Jets could appear aligned or symmetrical due to projection effects. Apparent stability in thrust and rotation could simply be below our sensitivity threshold. Periodic activity may seem synchronized only because our data comes from snapshot observations, not continuous monitoring. According to this group, Atlas may be more normal than it appears. The problem isn't Atlas, it's our viewpoint. 3. The unknown physics explanation. This is the most speculative but also the most intellectually honest approach. Some researchers argue that Atlas's behavior is too organized, too stable, and too consistent to fit comfortably within either natural extremes or observation error explanations. This framework doesn't imply anything artificial. It simply suggests that interstellar objects may operate under physical conditions, material properties, or internal structures that we have never encountered in the solar system. Perhaps, the extreme cold of interstellar space alters material strength. Radiation environments near other stars create different types of volatile compounds. Formation conditions billions of years ago produced ices or structures that do not exist here. Under this view, Atlas may belong to a new class of interstellar physics, a category we're only now discovering. Whichever explanation is correct, one thing is clear. Atlas is not behaving like a typical comet. And the deeper scientists looked, the more urgent it became to gather real-time data before this visitor left our solar system forever. As the list of anomalies surrounding 3I Atlas grew longer, the scientific community realized something critical. Time was running out. This object is moving quickly through the inner solar system, and its closest approach to Earth, December 19, represents the single best opportunity to gather data before it fades back into the darkness of interstellar space. Once it's gone forever. That deadline triggered one of the most coordinated astronomical campaigns in modern history. Across the world, observatories in the United States, Europe, Chile, Japan, and Australia, along with multiple space-based instruments, are preparing for synchronized observations. The goal is simple: obtain the most complete, high-resolution dataset ever collected on an interstellar visitor. 4 key measurements are at the center of this effort. 1. Jet velocity analysis. If the cyanogen jets are ejecting material at hundreds of meters per second, the natural sublimation explanation remains plausible. But if the speeds climb into the kilometers per second range, scientists will be forced to rewrite fundamental models of gas release, thermal gradients, and internal structure. 2. Advanced spectroscopy. Spectrographs will dissect the chemical signatures within the jets, searching for exotic compounds or unusual isotopic ratios. Anything unexpected, anything even slightly outside solar system norms, could reveal the environment where Atlas originally formed. 3. Surface patch evolution. High-resolution imaging campaigns will track whether the mysterious bright regions change, fade, or remain perfectly stable. Consistency would suggest deeply embedded volatiles. Variability might hint at fractures, vents, or rotating exposure patterns. 4. Long-term stability monitoring. Perhaps the most crucial measurement. Will Atlas maintain its impossible thrust stability beyond the current 182-day record? Will its rotation remain precise, or will it finally show wobbling and precession as physics predicts? Simultaneous observations will also provide parallax data, allowing researchers to reconstruct the 3D geometry of the tail and jets and possibly explain how these particles maintain their astonishingly tight formation. With every instrument primed and every telescope locked in, December 19 isn't just a date on the calendar. It is the moment the universe gives us answers or deeper mysteries. 3. I-Atlas is only the 3rd interstellar visitor we've ever been able to study in real detail, and like its predecessors, it refuses to behave the way we expect. Oumuamua challenged our understanding with its unexplained acceleration and bizarre, elongated shape. 2I Borisov appeared more comet-like, yet still carried chemical signatures that didn't fully match any object formed in our solar system. But Atlas is something different. Its anomalies aren't subtle. They're not borderline. They're bold, repeated, and structured long narrow tails, opposing jets, persistent antitails, and thrust stability that lasts far longer than physics predicts. Each of these interstellar objects is, in a sense, a physical sample from another star system, a fragment that has drifted through the galaxy for millions or billions of years before crossing our path. They are natural messengers, carrying information about conditions, chemistry, and processes that we could never observe otherwise. Whatever the final explanation for Atlas may be, extreme natural physics, observational illusions, or mechanisms we've never encountered, the object has already accomplished something remarkable. It has forced us to rethink what's possible. It has shown us that the diversity of material in the galaxy is far greater than what our solar system alone can teach us. And now, the question turns to you. What do you think we're really looking at? A natural phenomenon pushed to its limit, or a glimpse into physics shaped in environments far beyond our own? Share your thoughts in the comments. Every perspective helps expand this investigation. And if you want to follow every new development in the unfolding story of 3i Atlas, make sure to subscribe to CosmicFlux. This scientific investigation isn't over, it's happening in real time.